Hello everyone, in this video we're going to look at dissolution process of ionic solid. To represent this process, we have a picture right here containing 3 beakers, and they are representing a situation in which you have your ionic solid inside, which is typically a salt, and over time the water molecule that we have in there is what you are looking at represented in the circle. The water molecule, because they are polar molecules, they will start to dissociate the salts and they will start to make a homogeneous solution. The one in here in the middle bit, you can see that the process is starting to have all of the water molecule trapping or getting the salt components, okay, the negative charge species and the positive charge species will be attracted to the polar molecules of water. And then in the end of the process, you're going to have all of the charged species to be attracted to the polar molecules of water to form a homogeneous solution of the ionic salts. So dissolution process or solution process will involve the ionic solid, which is typically a salt. Okay, so here you can know that we can think that as a salt plus with your liquid water. And most of the ionic salts, okay, most of the ionic solids are soluble in water. So that is the thing that you need to know first. So most of the ionic solids are soluble in H2O liquid. And the reason is because H2O liquid, like what I have mentioned just now, this is a polar molecule. And the ions in the ionic solids can be separated from each other and converted to ions, like what you have seen here. In the beginning, you have the ionic in the form of solid. Okay, you have that in the form of solid. And the water molecules, they will start to dissociate all of the charged species that you have in the ionic solids, and they will become a homogeneous solution after a certain time. Try to recall the enthalpy of solution. This is very important when you want to understand what is going on for the dissolution process. So based on the definition of enthalpy of solution, the heat change when 1 mole of substance, over here we are going to refer to ionic substance. So we have KCl solid, and that KCl solid, this is an ionic solid. Why? You have K, potassium is the metal, and chlorine is the non-metal. So when you have metal and non-metal together as a molecule, ionic compound, we know that this is the ionic solid. And when you add with water, when you look there, the phases change to aqueous. When you add water, they will be dissociated. The formula for enthalpy of dissolution for the dissolution process is delta H solution equals to the delta H, or change in enthalpy for the lattice energy dissociation, plus the enthalpy change hydration. Or alternatively, we can have it written in this form as well. But instead of having change enthalpy for lattice energy dissociation, we will have negative delta H, or negative change in enthalpy of lattice energy of formation. The delta H lattice energy dissociation is defined as the heat absorbed. So you're going to absorb the heat in order for you to dissociate 1 mole of the ionic solid into the gaseous ions. Those are the keywords for delta H, lattice energy dissociation. The heat's absorbed. You want to absorb the heat in order for you to break all the bonds in the ionic solids, and then they will be converted into gaseous ions. So we can represent that situation by using these examples. Let's say we have sodium chloride solid. This is a very typical example of ionic solids. This is your table salts. We have been consuming this every day. So you have sodium, which is a metal, and chlorine, it's a non-metal. They are held by ionic bond between them to have the ionic solid. And when you put enough amount of energy, when you give enough amount of energy, what happened? They will start to dissociate into sodium plus gas and Cl minus gas. And how much energy do you need to do that? You need to have about positive 771 kilojoule per mole if you want to break the ionic bond between NaCl solid to make the gaseous ions. So these are the gaseous ions. Okay, so those are the gaseous ions. And when you look there, you have to absorb the heat. So we can say that the lattice energy of dissociation is going to be, in general, endothermic process. So when you have the lattice energy of formation, it will be the opposite of lattice energy dissociation. For this particular lattice energy, you need to have the heat being released, the opposites of dissociation. So you have to release a certain amount of heat in order for you to form 1 mole, forming 1 mole ionic solids. Just now, for dissociation, you need to absorb heat in order for you to dissociate 1 mole of ionic solids to make the gaseous ions. But this time, it's going to be the opposites. You want to form the ionic solids from the gaseous ions. Examples, we're just going to take the same example for sodium chloride. The process will be the opposite. So instead of having NaCl solids to be broken off into Na plus Cl minus, over here you want to form the ionic bond again. So this is the lattice energy of formation. When Na plus and Cl minus losing energy, so when they lost the energy, this one, they are going to lose some energy to make NaCl solids, and thus that is the amount of energy you need to give off in order for you to form the ionic solid. Some tip: when you have lattice energy increase, when you want to have the lattice energy to be increased, that will happen when you have ionic charges to be bigger. So the bigger the ionic charges, lattice energy will become stronger. And you need to have the ionic radius to be smaller. So if you have smaller ionic radius, you will be having a greater and stronger lattice energy. Okay, so if you want to have lattice energy to be increased, you need to have higher or bigger ionic charges, and you need to have smaller ionic radii. So this is some tip that you can try to remember. For example, the enthalpy change in lattice for magnesium oxide is bigger if you want to compare with the delta H lattice of sodium oxide. Why? Because when you have this here, because magnesium 2 plus is smaller, okay, it has a smaller ionic size, and it has a bigger charge than Na plus. That is obvious. Mg2 plus is in the group 2. Na plus or sodium is in group 1. So remember, going across a period, what happened to your size? The size will become smaller. And when you look at the charge, magnesium has greater charge, and sodium plus has a smaller charge if you compare with magnesium. So that is the reason that you need to know if they want you to compare the strength of lattice energy. Try to recall again. So ionic solids are between the metal and non-metal. These are the examples of ionic solids. So the one that I am going to highlight in black, those are the metals. So these are the metals right there. And the one in green, those are the non-metal. So that is ionic solid. And dissolution process, it's only concerning about ionic solids. If you look at both formula for dissolution process, you can use either one of them when you want to solve any problems related to the dissolution process. But when you look at both formula, we will notice that both of them will have the same delta H hydration. So what is enthalpy change of hydration? We have talked about this in the previous video when I explained to you about the 7 enthalpies. Just to recall on that, the enthalpy of hydration is defined as the heat release when you have 1 mole of gaseous ions hydrated in water. This is when you have your gaseous ion, like here, Na plus gas. And when you take that gas and you put that through water, it will be hydrated and it will become aqueous species. So this is what it meant by hydration. So hydration is going to be referring to the process of changing the phase of gaseous species to aqueous. Okay, you have another example right here for chlorine minus gas. So when you add water to it, it will become chlorine minus aqueous. Okay, so the process over here will involve the addition of water liquid. Now let's have a look at an example of question for dissolution process. In front of you, this is a typical question for dissolution process in which they're going to give you information about the hydration for the gaseous species, and you have the enthalpy of solution for the ionic solid. Number 1, the question wants you to construct the energy cycle diagram. So now you can imagine that this one has a relationship or related to the Hess's law. So you need to construct the energy cycle diagram. It's going to be exactly the same concept as what we have done for energy cycle method for Hess's law. This energy cycle diagram then will be able to represent the solution of NaCl. So how are we going to do that? Number 2, if you look at question number 2, it wants you to calculate the lattice energy of NaCl. This one, you will be able to do it after you have done the diagram. Okay? So the first thing that we need to do is, since you need to construct the energy cycle diagram to represent the dissolution process, we need to start with writing the lattice energy equation first. Okay, so the lattice energy, you can pick either you want to do it in the form of formation or you want to do it in the form of dissociation. I prefer to do that with dissociation. So let's start by writing. Okay, so step 1. Step 1, we're just going to write the lattice energy. Okay, so we're going to write the equation for the lattice energy of NaCl, and that is NaCl solid dissociates to form Na plus gas plus Cl minus gas. So this is the process for lattice energy of dissociation for sodium chloride. And based on the question, this is the one that we need to find. So that is the lattice energy. So this is the one that we need to find out. And what does the question gives to you? So it gives you hydration of sodium plus. So that is, okay, the one in yellow, we have hydration. So you have Na plus gas. Okay. So that one will be hydrated and changes to Na plus aqueous. So you don't have to write water into that. It will automatically, people will know that this one is for hydration of sodium plus the one that you have on top. And the energy is delta H. Okay, hydration equals to negative 390 kilojoule per mole. Second, or rather third, is hydration of Cl minus. So the hydration of Cl minus should be Cl minus gas, and you'll have Cl minus aqueous, delta H hydration, then negative 380 kilojoule per mole. Okay, and lastly, for solution, so you have the enthalpy of solution in purple. So solution is when you have the solid NaCl. This one is a little bit similar to what we have on top for the lattice energy over here, but this is when you have the NaCl solid. When we have the NaCl solid, you're going to add water directly. Then it will become Na plus aqueous plus Cl minus aqueous. So that is delta H solution plus 6 kilojoule per mole. Okay, so what you have here for all of this, for this solution, you have H2O being added. Same goes to the one in green, hydration. For Cl minus, you have H2O being added, as well as right there. Okay, so they have water involved in this process. Now we have written down all the thermochemical equation that you need to construct the energy cycle diagram. So if you want to construct the energy cycle diagram, it's better for you to write this one first. So essentially, this is your step number 1. Okay? When you write all the thermochemical equation that you're going to need. So step 2. Now we're going to construct the energy cycle diagram. So we're going to write the first line on top over here, and that will be the lattice energy. So the lattice energy would be NaCl solid. So this is the one that we want to find out. It will change to Na plus. Remember, gas, don't forget the phases. Phases is very important. Cl minus gas. And we have, when you look here, you have the solution. Okay, you have the solution process for Na plus Cl minus there from NaCl, and that is plus 6. So you can start from there. I'm going to do that in purple. So this is the enthalpy of solution. We have Na plus aqueous plus Cl minus aqueous. Okay, the one here, this is the third one there. Okay, the fourth one, I'm sorry. So you have the first one, second, third, fourth. The purple bits over there, I have written that down here. Therefore, the energy for that is positive 6. So you're going to put, this is positive 6 kilojoule per mole. And when you look at this, gas to aqueous, it resembles what you have there, gas to aqueous. So gas to aqueous, the one in yellow, that is the hydration of sodium plus. So we're going to use yellow. So the value of that is about negative 390. So you put negative 390 kilojoule per mole. And we have another one right there. Sorry, that should be in green. Okay, for you to know that this gas to aqueous hydration over here is for that. Okay, Cl minus gas, water, Cl minus aqueous, then you have the hydration as what you have there, and you have negative 380. So that is negative 380 kilojoule per mole. When you construct this table, you will get 1 mark for this, correctly written, together with the value there. 1 mark for this, and 1 mark for that one. So you get this one, 1 mark, that one, 1 mark, this one, another 1 mark. Okay? So, in a way, what you have right here, that is the target equation, like what we have done in the previous Hess's law exercises. So that is the target that we want to get. And we should be able to find that. So how do you find delta H LE? How do you find this? Remember the formula. Remember just now when we talk about the formula for dissolution process, we have two. We have delta H solution equals to the enthalpy change in lattice energy dissociation plus delta H hydration, or you can use the negative delta H lattice energy formation plus delta H hydration. In the cycle that we have constructed, the lattice energy that we are using now is lattice energy of dissociation. You have to remember that. So that right now, this is for dissociation. So when that is dissociation, the formula that we're going to be using is, so the formula, the solution now equals to delta H lattice energy dissociation plus for the hydration process. Those are hydration, and that is for the solution. So when you use this formula, what you're going to be getting now, you're going to substitute this into there. Okay, so we're going to substitute this solution with this. So you get 6 kilojoule per mole. And we're going to substitute those two into the hydration. You're going to substitute in here, and you'll get negative 390, negative 380. Okay. When you move this to the other side, when you solve this to get the lattice energy of dissociation, you will get therefore the lattice energy dissociation equals to six plus 770 and the answer is plus 776 kilojoule per mole. Okay, so that is the answer. In terms of marking, you will get 1 mark for this. Okay, 1 mark for the formula. Let's have a look at the second question. This one gives you the lattice energy of sodium fluoride, NaF, is negative 902.4 kilojoule per mole. And that is a very important information because you have a negative lattice energy. Therefore, this one will be lattice energy formation, okay, not dissociation. And if the enthalpy of solution is plus 19.8 kilojoule, determine the enthalpy of hydration of F minus given the enthalpy of hydration of Na plus is negative 424 kilojoule per mole. You have quite a lot of information in a short question. And how are we going to do this? So when we want to find the enthalpy of hydration, we have to construct the energy cycle for dissolution process. Step number 1, we have to write the thermochemical equations just like what we have done in the first example. So these are the thermochemical equation that we have. I'm gonna try to highlight the one that is important here, especially for number 1. What you look at this equation now, this one is representing lattice energy of formation. Why? Because the question gives you the lattice energy formation of NaF, a negative value over there, negative 902.4 kilojoule per mole. So that is the reason why we're going to write it in this form, because we want to form the ionic solid NaF from the gaseous species. If you are given lattice energy positive, that one will be lattice energy of dissociation. When you look at this question, it is slightly different from what we have had done in the first one. In the first one, it asks you to find the lattice energy. It doesn't mention specifically whether it's going to be formation or dissociation. Thus, it's up to you to decide. But in here, the question gives you lattice energy of formation. We have to note that the question gives lattice energy in negative, and for that reason, we have to treat that as lattice energy formation, and we're going to write the thermochemical equation like so. Moving on to yellow, green, and purple. Number 2, yellow. This is the hydration process of sodium plus, right here. Okay. And the one in green is the one that we need to find. We need to find the enthalpy of hydration of F minus. So that's why we do not have the value over here yet. The one in purple, number 4, is the solution. Okay, you have the enthalpy of solution, which is 19.8 kilojoule per mole. And this is how you're going to write the thermochemical equation, and you have the value right there. We have all 4 thermochemical equations you need to have. Next, what you need to do is you need to construct the energy cycle for this. Step number 2, constructing the energy cycle. We're going to start with the lattice energy formation on top, just like what we have done previously, but that one is going to be dissociation. That's okay. And then that, once we have done that, we can cancel that out. And now we're going to try to do this one, the purple bits. Okay, solution. So that one should be from here, solution, going to that side, and you'll have F minus aqueous and A plus aqueous. And the value, as you see here, is 19.8. Just going to write it there. Plus 19.8. Don't forget the units. And that one is considered as done. Now we're going to move on to the yellow and green. These are the hydration. So sodium is the one in yellow. So that is right here. This is negative 424 kilojoule per mole. And the one that we need to look for is this. So that one is delta H hydration. So when you do this in exams, you'll get 1 mark for this, 1 mark for that, 1 mark for here, and 1 mark for the one on top. Now, the energy cycle is completed, and what we need to do now, we have to calculate what is the value of delta H hydration for F minus. So we have done that one, we have done that one, and next, since the question gives you delta H lattice energy formation, we have to use this formula. Remember, we have two formulas for dissolution. Since the question gives you lattice energy of formation, then we need to use delta H solution or dissolution equals to negative delta H lattice energy formation plus the heat change in hydration. So when you do that, we're just going to substitute the value of which that you have given what you have in the thermochemical equations. You're just going to substitute in here one by one. And finally, what you will be able to do is to find the delta H hydration of F minus equals to negative 459 kilojoule per mole. So you'll get 1 mark for that and 1 mark for the equation that you have used.